Hello, everyone, and welcome to today's exciting webinar. I'm Tim Stark and the host of today's exciting event. I'm a professor of civil engineering at the University of Illinois at Urbana-Champaign and the technical director of the Fabricated Geomembrane Institute here. This is our third webinar of 2020, and the remaining 9 webinars for 2020 have already been scheduled with great speakers and timely topics, which I'll show on the last slide today. During today's webinar, we welcome questions and comments which can be typed into the questions box in the control panel. You may send in your questions at any time during the presentation, and our speaker will address them at the end of today's presentation. The recording of this webinar and a PDF of the slides will be made available on the FGI website after today's presentation. PDH certificates will be sent automatically to all of those who attend the entire webinar. Today's webinar speaker is Terry Sheridan. Terry is president of GeoStorage Corporation based in New Jersey. Terry worked in the construction products and geosynthetics business before founding GeoStorage Corporation a little over 10 years ago. Today, Terry will focus on stormwater management and underground geosynthetics-based systems. The title of Terry's webinar is Stormwater Management Using Geosynthetics. Terry, thanks for squeezing this webinar into your busy schedule and joining us from Rumson, New Jersey. The webinar controls are yours, Terry. Thanks.
Thanks so much, Tim. Thanks, everybody, and welcome. As Tim said, I'm Terry Sheridan. I graduated Villanova in 1983, College of Engineering, Civil Engineering. Worked for 5 years for Contech Construction Products. The following 16 years at Tensar Corporation in the environmental department before founding GeoStorage Corp. Well, now this up and down didn't work. Let me just
page down.
Page down is what I'm hitting here, Tim. It's working fine before.
Yep, turn off your.
Is that? Here we go. I very much apologize, everybody. Here you can see in the July edition of Geosynthetics magazines, one of our first jobs, July 2010. So we've been working on this geosynthetic-based system and over the last 10 years. And here are some of the developers, engineers, and contractors we've worked with across the country. The fundamental rule of stormwater management is that the flow rate off of your developed site after you complete construction cannot be higher than the flow rate off that site before you started construction. Typically, that's done with a detention pond, but where the land is valuable, you will put that underground to save the space, and it's typically below a parking lot. Here you can see a schematic of the geosynthetic-based system that we're going to talk about today. Essentially, you have a large open chamber, in this case, 2 chambers are illustrated. That chamber, a large open chamber, stores water. It is formed by geosynthetic reinforced stone walls. That stone backfill is an open graded angular stone that has 40% porosity. So you are creating a very large open chamber, and everything you're using to build that chamber has 40% porosity. In addition, the walls of that chamber are an open graded aggregate stone that will facilitate flow into that stone bed, and that'll be a helpful feature, as we'll see later. The chamber tops are topped with a reinforced concrete slab with traffic loading strength, And the entire system, ceiling, floor, and walls is enveloped in a geosynthetic liner. In the case where we're infiltrating the water, that's a geotextile. And in instances that we will talk about, we will also use a fabricated geomembrane. The design of the system is based on the FHWA integrated bridge system, which you see in the upper right-hand corner. We're following the same design procedure that would be used for a federal simple span bridge on an interstate. Same service life, factors of safety, loading conditions, and the like. In the upper right-hand corner, you'll see a unique feature that the FHWA was able to incorporate into the integrated bridge system. Previous to that, and our system also meets, and this goes into the weeds a bit, mechanically stabilized earth wall design procedures. But the integrated bridge allowed for the bridge superstructure to be placed directly on the reinforced abutment. And that greatly simplified and reduced the costs of construction. And how is the FHWA able to do that? Well, they have deep pockets, so they tested that placement of the bridge superstructure on the bearing seat. And what they found was the limit of their testing equipment got up to 13 tons per square foot for the bearing capacity of that bridge seat. And they were unable to fail that bridge seat bearing area. They did see some hairline cracks in the masonry blocks at the face of the abutment wall at around 4 tons per square foot. And they put a factor of safety on that, and the the IBS systems, as well as the geosynthetic-based storm water detention systems, are based on a maximum bearing capacity of 2 tons per square foot, which, as you can see from this photo and from that 13-ton ultimate limit, is very, very conservative. Another feature of the system is that large open chamber enables access for inspection and maintenance crews. Not only do they have access, but they have direct contact with the infiltration floor. It is not buried below structures or a stone bedding, so they can examine it and potentially remediate it if that was necessary. This access is different than a lot of other underground detention systems. In the right-hand corner, you see one way that they might be inspected and maintained, and obviously where access is where you're incapable of putting people into the system, it's a remote access, and it's a little more complicated and difficult. In the bottom left-hand corner here, you'll see a table that was developed in a paper by some Drexel professors that provides the carbon footprint for all of the detention systems in the marketplace. And at the bottom, you'll see that the underground chamber with geosynthetics had the lowest carbon footprint. This is a nice feature. It really hasn't amounted much to in the field, but I thought it was worthwhile to point out. Now, when you're dealing with an underground or any a pond or an underground detention system, there's really two things, two applications that you can look at: infiltration and detention. Generally speaking, regulators and engineers are trying to infiltrate the water. If the soils allow, infiltration will allow the soils to clean up the contaminants of the water and replenish the underlying aquifer. However, if the soil doesn't allow it, or if there's other reasons for not wanting it, you have detention, where you just outlet it to the outlet control structure. The fabricated geomembranes would be used in certain applications where you're trying to get detention. Contaminated sites on urban infills, you don't want that infiltrating water to carry the contaminants down to the aquifer, so you'd line the site. Karst geology, you don't want the infiltrating water to create sinkholes in the limestone geology. Highly porous geology, where you have bedrock with cracks, is an example. You don't want to have the infiltrating water moving so quickly through the subgrade into the aquifer that it doesn't have time to treat the water. So they would possibly line that. Rainwater harvesting, where you're going to create a reservoir for the water to reuse it, is another application. Gets a lot of press. Frankly, it's not used as much as you might read about it, but we will talk about one pretty large rainwater harvesting application in this presentation. And lastly, stormwater treatment applications. We'll look at where geomembranes are used in that application. Here is one of our early jobs in Camden, New Jersey. Camden is an older city on the Delaware River across from Philadelphia that has a combined sewer, meaning that both the sewage and the stormwater use the same pipe network that flows to the wastewater treatment plant. When you have a heavy storm, you can inundate that wastewater treatment plant and cause a CSO, or a combined sewer overflow, because of the heavy rains and the lack of capacity at the wastewater treatment plant. And everyone is trying to avoid CSOs, or combined sewer overflows. One of the ways to do that, upstream detention ponds to restrict flow into the pipe network and down to the wastewater treatment plant. In Camden, they require a geomembrane on every stormwater detention system that is connected to their combined sewer network. Here you can see a 30 mil PVC liner that has been placed on the floor and the sides of an underground detention system. We're going to build a geosynthetic based system above. First order of business is to boot the inlet and outlet pipes that protrude through the liner system around the perimeter of the excavation. The pipes are extended from the perimeter to the chamber, and the walls are built around that chamber. Welded wire forms are used at the face of the wall. Struts are used at 2 foot on center to stiffen that welded wire L bracket to allow for placement and compaction of the stone behind it. Geosynthetic reinforcement, in this case you'll see geogrids are placed to reinforce the stone abutments. They're placed in 9-inch lifts in conformance with the IBS standards. The geogrids are wrapped at the face in a technique that many of you are probably familiar with called wrap face geosynthetic walls. And the operation continues to the top of the abutment. The pipes are extended through the perimeter liner, through the reinforced abutment, through the chamber wall into the chamber. Here you can see the geogrid wrap face at the face of and behind the welded wire forms that holds the stone back, and it's tucked in around the pipes to ensure that the stone does not ravel into the chamber. And that, along with the stiffening bars, allows for compaction equipment to compact that stone right up to the face of the chamber wall. Here you can see them preparing the chamber for the reinforced concrete roof plank, which is being placed right here. One of the questions I ask is, what are the dimensions of the chamber and the roof? And the easy answer is, they can be designed for any dimension. The IBS system allows for simple spans up to 140 lineal feet, bridges with that kind of clear span. In this case, what we look at is the roof is the most expensive component of the system. And so we try to design that as efficiently as possible and then fit the chamber size around that efficient design. In this case, the roof is 20 feet, 6 inches long. And the reason for that is rebar is manufactured in 60-foot lengths, It's stocked in 20-foot lengths, and we have a 3-inch clearance on each side. So we're using a 20-foot rebar with a 3-inch clearance on each side that gives us a 20-foot, 6-inch roof out-to-out span, and leaves us with a chamber clear span of 14 feet. That allows for a 3.25-inch bearing surface, which keeps us under the 2 tons per square foot limit that we have set for ourselves with the live and dead loads that will be supported. In our narrower chamber, we'll use a 10-foot rebar that will result in a 10.5 foot wide roof and a 5.5 foot clear span chamber. Within these roof planks, we will leave a manhole designed for a manhole. That manhole can be an inlet grate with a water treatment insert in it. At the top, we'll put a splash pad at the bottom of riprap. That will save a good deal of money over a concrete manhole structure that it would replace. Sometimes it is simply an access manhole, and in order to bring it to the surface, we'll use concrete construction rings or concrete grade rings that are commonly used out there, and the laborer is well versed in how to bring a manhole to the ultimate surface elevation of the grate or the lid. We then typically, or we always cover the system, and I get asked, can you use the system where the concrete lid is at the surface? And the answer is you could. However, you then have to treat the joints, pretty them up, so to speak. You'd have to also do the same with the transition from the asphalt to the concrete lid. Most importantly, parking lots and streets and the like are typically built at a grade for drainage purposes, and you would have to build the system to the grade of the street, which is pretty exacting. Much easier to simply bury the system, take those costs and those challenges out of the picture, and we usually try to bury this system at a depth equal to the road base cross section of asphalt and structural fill. That's going to be somewhere in the 9 to 12 inch range. Nothing new here. System completed with the asphalt placed on top. One more asphalt layer looks like it's going to be placed to get everything to grade. Along with the wet cast systems that you saw in the previous application, we also use a product called hollow core planks. These are pre-stressed planks manufactured in a facility. Obviously, they have hollow cores, as you can see, and as the name would indicate. And they're very, very cost-effective and efficient. The challenge is there's only so many hollow core plants across the country, and only a certain number of them manufacture the 12-inch deep planks necessary and robust enough to handle the HS20 traffic loads. So we try to use them where we could. We use a lot of them in Southern California, but you're limited by the locations of the factories and what they produce. Another application we see here is at Marion Golf Club outside of Philadelphia, host to the 2013 US Open. I think that one was won by Justin Rose. This is a water harvesting application. So clearly we want to use a geomembrane to hold that water in this reservoir, which is going to hold 100,000 cubic feet of water in 3 chambers that are just over 9 feet high. In this case, you're seeing a telebelt delivering the stone to the abutment walls because we only have access on one side of this system They did not want us bringing equipment on the fairways, and the creek that they're taking the water from is on the far side of this system. So telebelt is neat. It can be expensive. So the typical tools that we use for the placement of the stone is an excavator pulling around a rock box that is fed by a front end loader and rotates around the system placing the stone. Here we can see the concrete lids being placed, in this case by a crane. Once again, we try to use the excavator that the contractor has on site to excavate the hole to pick and place the concrete lids. And that's what we do most of the time. In this case, accessibility and the size of the system required us to bring in a crane. The pump house that is the center of this whole operation to store water on site and use this reservoir to water their fairways. The pump house will be placed on the right side, right hand side of the middle chamber here, above a sump that is actually lower than the floor of the rest of the system, where pumps are inserted into. So it is a neat job. It's always fun to work on a job like this. You can see the 10th fairway in the background, one of the famous creeks running through Marion on the right side where they're pulling the water from. And the reason they wanted water harvesting on this job was that they were afraid that if drought conditions hit Philadelphia, the Philadelphia Water Department might restrict their ability to water their fairways. So they went through and built this system. Next slide here looks at, the basic reason why you might want to consider a geosynthetic-based system when compared to all the other products out here. And we'll kind of give an overview of them here. This is a cost per cubic foot slide where the costs are on the y-axis and the depth of the system, which influences costs, is on the x-axis on the bottom of your system. The most expensive component, or the most expensive underground detention system, you can see in the upper right-hand corner, precast concrete vaults. The dollar per cubic foot you see here is a few years old, so it might be outdated a little bit, but I think the relative costs are what we're looking at, what you want to take away from here. And here it's just over $8 a cubic foot for the materials on a precast vault, including the stone bases and the stone side slopes. Now, precast vaults are well engineered. Many of the engineering techniques that you're using for the vault are what we use in the development of the concrete lid for the geosynthetic system. Being expensive, you don't see them often on residential and commercial developments. Those owners are particularly cost conscious. But where do you see them? You would see them on a site where nothing else fit. An urban infill where you have a lot of infrastructure in place, you have a limited footprint to work in, and the precast concrete vaults fit. You might also see them in applications where you have an export site, especially if the export is contaminated. That cost to export that material could offset the higher cost of a smaller system. So you would see them in that sort of application. Same thing can be said if the foundation was bedrock that you weren't able to rip. It's expensive to blast or take that bedrock out by other means. The smaller footprint and the smaller excavation area of something like a precast vault might come in handy. On the left side here, you see high-density polyethylene pipe system. High-density polyethylene pipes, when I started in this business, were manufactured in 6-inch to 12-inch diameters. And over the course of my career, they're now manufactured in this country up to 5-foot diameters. So they have gotten quite large. They are flexible pipes. They rely on two engineering principles for their support. That is ring compression and soil arching, which transfer the loads from the pipes into the surrounding soil, which is going to be a structural fill because it's going to be carrying the load. And high density polyethylene corrugated pipe structures. The pipe itself is less expensive than the corrugated steel pipe in diameters below 36 inches. And that's why the pipe has displaced a lot of corrugated steel pipe across the country over the last number of years because of its lightweight and being relatively inexpensive in the lower diameters, which is the predominant diameter size for stormwater detention or stormwater management applications. To the right of that, we see plastic modules. You might hear a euphemism for them, plastic milk crates. They are still relatively expensive. They need you're gonna need to be careful when you're installing these to make sure the floor is absolutely flat and that they are absolutely vertical during construction. I would, the designs are based on laboratory testing and manufacturer's recommendation. There's no standard out there for the design with these structures. And if they're placed under a traffic load, I caution you to be careful with the design. In the middle, you'll see here, I should use the pointer here, is a plastic pipe arch. These are half-round pipes. So because you no longer have to compact underneath the haunch of a pipe, you can place these pipes, these chambers closer together. Spacing of 6 to 9 inches is typical. They're backfilled with open graded stone, so you're getting the porosity of the stone, and wrapped in a geotextile to separate the or a geomembrane in the cases that we pointed out. They do not have the full diameter ring of a pipe, so they don't have full ring compression. So their ability to carry overburden heights, their strength is a little less than you'd see for pipes. It's a little more limited on what the overburden will carry. They're typically used in lower profile applications. Next, we'll go on to corrugated steel pipe. This has been the pipe has been used the longest for underground stormwater detention. It can be manufactured up to 144 inches. And as I said, it's less expensive than plastic pipes after you get in that range of 30 to 36 inches in diameter. However, you cannot, unlike HDPE pipe, which you can perforate and backfill with an open graded stone and get the added storage capacity of that stone, corrugated steel pipe is coated with, in the early years, galvanized coatings. In the last number of decades, it's more typical to see an aluminum coating to protect the base steel against corrosion. If you perforate the pipe, you're going to expose the base metal around each perforation, and you'll have accelerated corrosion around every corrugation. And that's particularly of concern in northern regions where you'll see de-icing salts used on the roadways and will make their way into your detention system. And you don't want to have exposed base metal throughout your pipe and accelerated corrosion, decreasing your service life. And the last system here is the geosynthetic system that we talked about. And as you can see, it is less expensive and offers significant savings when compared to all the other systems. You can see that as the depth decreases, the cost per cubic foot of storage increases, as it does with the pipe systems and the like. And so that is typical. And we're going to look at the reasons for that and how it impacts the efficiency of the system. So the first question is, what are the sweet spots for the geosynthetic system? Where do we offer the most savings? And that would be two applications, one with a deep profile. And the simple reason for that is that the roof, being the most expensive component, costs the same whether it's spanning over a 3-foot deep or a 12-foot deep, as an example chamber. It costs the same, but in the deeper system, it's storing 4 times the amount of water. So it becomes very, very efficient as you get to deeper and deeper profiles. In the bottom, you'll see a low profile system with a large available footprint. This is something I didn't recognize in the early years as being an area that we offer, or that geosynthetic based system offers significant savings. But the porosity of this backfill stone and the area of the chamber walls make this a very cost-effective system. And let's look at the reason for that. Here we can see a graph showing the average national cost to store water in different diameter corrugated steel pipe system. These numbers are from 2006, so they're 14 years old. The numbers aren't nearly as important. They're obviously going to be higher today. That's just the relative cost that we'll talk about. So at the bottom, you can see a 96-inch pipe, 8-foot diameter, roughly $2.42 per cubic foot to store water in. If you move to a 48-inch pipe, you can see that the cost to store water in the 4-foot diameter pipe is twice as much. And if you move to a 24-inch pipe, the cost to store water in the 24-inch pipe is 400%. So we're not talking about incremental savings as you get to a lower and lower profile. As you move to a lower profile, the costs increase dramatically. Even 3 to 6 inches differential in the available profile height can have a big impact on your budget. So what I'd like to think of as a counterintuitive misconception out there is that stone is expensive. It is in fact expensive, and contractors and engineers recognize that intuitively. If you are comparing it to general fill or even structural fill, you can pay a premium for angular open graded wash stone. However, in the context of stormwater detention, particularly low profile stormwater detention, stone is extremely cost effective. Now, across the country, the stone prices can vary, but as a general rule, I'm just going to point out an area: North Carolina to Maine, out to Ohio. In that area, stone prices would typically range between $15 and $20 a ton. Most of you will know what it costs in your region, but that covers a great deal of the country, that sort of range. And here you can see in the bottom, if you just recalculate that, $18 a ton, convert that to dollars per cubic foot that you're paying for the stone at 90 cents, and then recognize that you're getting 40% porosity out of every cubic foot. What you see is the cost to store water in stone is $2.25 per cubic foot. On today's basis, that's what you see. And when you compare that to 14 years ago pricing on 24-inch or 48-inch pipe, you can see the savings can be 50 to 75%. So stone is very cost effective in low profiles. Well, how can you use the stone in the geosynthetic based system? First thing you look at is, well, what's the coefficient? We know the porosity is 40%. What's the coefficient of permeability? For 1.5-inch stone, which is the backfill we will use, it's 7.9 feet per second. Here, and Tim will probably like this slide, Darcy's law. It might not be something you use every day, but it's really quite simple. We won't go through the derivations here, but we'll take the example and see what the end result is. Here we have on the bottom here, we're going to use a 5-foot wide chamber. It'll be 5 feet high, and I'll have a stone bed of 100 feet on each side. This is a very, very large stone bed. But when we go through Darcy's law and take the hydraulic conductivity times the surface area times the, let me get this right, times the hydraulic gradient, we realize that along the chamber wall, we have a permeability or an infiltration rate of 2 cubic feet per second per lineal foot of wall face. And my apologies here, at some points, infiltration, permeability, and percolation might be interchanged. They are different, and you want to be careful that you don't interchange them. My apologies if I do that in this discussion. We see that the chamber wall has 2 cubic feet per second. And if we look at a 100-year storm event at 50 cubic feet per second, we ask ourselves, how big a chamber do we need? Well, 50 cubic feet divided by 2 feet is means that we need 25 feet of 25 lineal feet of wall. We have the two ends of a 5-foot high system on our narrow plank that'll be roughly 5 feet wide, and the chamber length is going to have 2 walls on either side. That leaves us 14 feet required divided by the 2 walls. We need a chamber that's simply 8 feet long and 5.25 feet wide to handle this very large storm event and ensure we don't have a choking point within that chamber, a choke point. In other words, the water that flows into that chamber at 50 cubic feet per second can flow out of that chamber at 50 cubic feet per second per Darcy's law. Now, you might say, hey, can we do that with other systems? Well, let's look at a pipe system, which has different features than the geosynthetic wall. Here we have a 60-inch pipe. And what is the perforation size along the length of that pipe? What you see is there's 2 square inches of open area for the perforations per lineal foot of pipe. Just on a quick observation, if you have a 5-foot high chamber, per every lineal foot of pipe, we have over 1,400 inches squared of stone face. So right away, you can see this is going to be a big, there's going to be a big difference in the design. Here we have the perforation equation, and essentially it tells you what is the flow through each perforation, and when you have 2 inches per lineal foot, what is the cubic flow out of that pipe for every lineal foot. And if we use the 50 cubic feet per second, 100-year storm again, we see that you require over 1,500 lineal feet of pipe to ensure that the water running into the pipe at 50 cubic feet per second runs out of the pipe at least that fast, so you don't have a choke point that will mess up your hydraulic model and your stage storage volumes. So does this geosynthetic based system work everywhere? No, it doesn't. It doesn't work if the stone is expensive. It'd have to be very expensive, frankly, but places like Long Island and southern Florida that the stone doesn't exist and it's expensive to get there, probably not going to work there. Small footprints. The stone is going to take up a large area. We need a large area for it to work. And so if you're limited in your area, this is not an option. And as I said before, there's another one where export sites, where if you're paying, and particularly contaminated site, paying for export, that can outweigh the savings you're seeing by using the system. Now we'll move on to stormwater treatment. Stormwater treatment is the other side of the stormwater management business. We just talked about stormwater volume. Now we're going to talk about treating the water. In ponds, you treat the water traditionally just by sedimentation and by infiltration or running it through a sand filter. That's the most commonly used filtration system out there. However, if you're trying to use a sand filter and you're going underground, you're going to have to get a certain surface area of sand to make it work. And it may require a very large concrete precast vault, which, as we've seen, is expensive. So manufactured water quality devices have been developed. This is a vortex system, basically spins the water around inside the chamber and enables the sediments and the total suspended solids, at least the larger ones, to settle out into the sump pit at the bottom of the chamber, which can be easily removed by a vac truck dropping a hose down into it. This manufactured system has the ability to take out a certain amount of suspended solids. If it does not take out enough to meet the local regulations, you'll have to go to a system that is upgraded and is more efficient in removing total suspended solids. And that's an area, frankly, that is a wild west of arguments out there about testing and the like that I don't know that they still come to grips with. But here you can see what I'd call a cartridge system. It's housed inside a concrete vault. Each cartridge has a surface area that you can infiltrate through. The cartridges are filled with treatment media, and the water runs through that treatment media into a standpipe and down into a header and off to the outlet control structure. These systems are remove more sediment as a percentage than the vortex systems. They are more expensive and they are harder to maintain. You've got to get those cartridges unscrewed and up through the manhole, so it's not quite as easy as taking the vac truck. What do we do with the geosynthetic system? Well, our system is pretty simple. We simply add a sand filter to the floor of our chamber, which is just inherently available from the design of our system. So you would just go to the typically the state regulations. You would find what sand filter gradation is required for your filter, and there would be an equation there, a simple equation to say here is the surface area required for your sand filter given the storm event that you're working for. And you would calculate the surface area to require and size your chamber accordingly and place the sand filter in the floor of the system. Your costs are really simply that of the sand. There's a little bit of pipe, a few extra grids to support the foundations of the walls around it. And it is a very cost-effective and efficient means of getting water quality. And it's a high-end water quality of a sand filter. It should be just about all of even the most stringent codes. Here you can see one being built with the sand in place, the sand pipe that is used to clean out the collection pipe that is at the bottom of the sand filter and runs to the outlet control structure at the end. And these systems are typically 18 inches deep. Here you can see another system, the standpipe in place. Interestingly, totally different color on the sand, but still meets the same criteria as the previous slide. That may be an inlet or outlet control pipe you see at the end. And basically what you're doing is sizing or locating your outlet pipe invert at a level that below which provides the storm water quality control volume that is necessary. And until that volume is hit and the water runs out of the geosynthetic system, it is forced to move down through the sand filter system. So very simple design, very economical. It's probably the highest growth portion of our business. One of the things about it is it's almost impossible to include after the fact as an or equal because it's a totally different design system. And like I said, it's contentious how they evaluate these systems. So just in summary, the geosynthetic based system, very cost effective. It's based on FHWA bridge guidelines, so a high confidence level from the engineering community on both the service life, the loads being used, the safety factors are all designated by the FHWA. We are not relying on manufacturers' recommendations and testing. The design allows for complete access for construction equipment. I have a number of contractors who like to use it simply because when they leave the site, they're not worried about the people who are going to build a building afterward running over and crushing the system. It's very robust, and they don't have to worry about having to rebuild it because some equipment crushed it. It maximizes flow into and through the stone, and that's in the low profile systems, is an important feature. It has the smallest footprint, or it can be designed with the smallest footprint, with the exception of the concrete vault. It's also accessible for inspection and maintenance crews, has the lowest carbon footprint, and we can add the sand filter inexpensively to handle water quality requirements. Now we'll move on quickly to the some geotechnical engineering challenges I see in the market, and I'll ask Tim to focus here, and I'd love his opinion at the end on things that I've seen out there that I think could use some further research and commentary. Infiltration. If you're going to use infiltration and count it in your design, the EPA is going to say the minimum allowable infiltration rate is 0.5 inches an hour, half an inch an hour, and most states are going to incorporate that half inch per hour. For the Fabricated Geomembrane Institute, I think most of you will recognize this slide. It is the EPA's minimum guideline for capping solid waste landfills. And you'll recognize the cover requiring a maximum infiltration rate of 1 × 10⁻⁵ centimeters per second. When you convert that to inches per hour, it becomes 0.014 inches per hour. Okay, let's compare those two. As you would expect, the infiltration through the landfill cap is over an order of magnitude less than the minimum allowable for infiltration, as you would want to see. You don't want water infiltrating into your landfill cap. Here's the issue that I observe from my history in the market and in the environmental market. In my experience, it seems that on landfill caps, owners and contractors are able to get on-site or local soils to meet the maximum allowable infiltration rate of 0.014 on landfill caps across the country. And as geomembrane people, I think you probably see the same thing and look and say, well, yeah, I wish the market, they weren't able to do that so often. And it seems that they're able to do it everywhere and every time. That's my perception. And that makes me ask the question of, if on-site soils are so routinely able to meet that requirement, where in the heck are you going to be able to find soils that are going to meet the infiltration requirement of stormwater regulations? So I looked into it further, and you can see at the bottom here, taking 0.5 inches per hour and converting it, it comes to 7 × 10⁻⁴ feet per minute. Now we look at this chart for typical properties of soils, and what we see is that only 4 soil types meet that flow rate. I'm saying flow rate, infiltration rate. Once again, I apologize if the nomenclature is a bit off. And not only do the other soil types not meet it, they're not meeting it by 1, 2, or 3 orders of magnitude. Now on the top, you'll see this is noted as compacted soil, which is an important characteristic to note. If we look further on those 4 types of soil types, what we'll notice about them is, well, number 1, they were compacted, as I said. Number 2, they have less than 5% fines. Well, where are you going to find soils that have less than 5% fines? Those of you who are designing walls in the marketplace probably recognize very rarely our on-site soil is going to have, you're going to be able to use as a backfill when the fines content requirement is so low. So this might be kind of understood by many of you by just the markets that you're working in. But here you can see finding soils that have less than 5% fines is generally very difficult. It's also another reason why the flexible pipes that we looked at that require a structural backfill almost always require imported soils for that backfill, because on-site soils are going to have too high a fine content to use. Here is some more work that kind of solidifies this issue or is another touch point to look at. Work done by a colleague of Tim's. You can see the 1/2 inch an hour line up here for the coefficient of permeability. And what really is important to note here is look at the impact of higher percentage of fines, as defined as passing the 200 sieve, and what it does to the coefficient of permeability. In stormwater design, it's typical to apply a factor of safety of 2 to your infiltration rate to cover safety factors. But if you look here, the range over what I would consider small changes in fine content, it's not 10-fold, it's not 100-fold, it's 1,000 and 10,000-fold, as well as the different types of fines you might have would impact that permeability. So this 1/2 inch per hour, I just am curious about how long we can count on it for when it's measured out in the field. And one of the other things to consider here is that the rates you see, even in this graph, are for compacted soils. And the range, I think, with compacted soils, which non-compacted soils, can be dramatic and might explain why we were able to test and meet this 1/2 inch per hour criteria. But when you have a large infiltration area, there's a limit to how much you can excavate with a long stick excavator from the sidelines. Many of them are too large to do that. And practically, most jobs are going to have equipment in the hole, or do have equipment in the hole. In addition to that, you can compact soils mechanically or hydraulically. And by definition, an infiltration application is going to continuously compact the soils hydraulically. One other factor is the stone you're bringing in for your infiltration bed. It has a dust on it. And also the storms are going to bring with that water suspended solids with them. Even with upstream water quality devices, there's going to be a certain percentage of suspended solids. And over time, those fines, that dust is going to percolate down to the surface of your infiltration floor. And lastly, if you look at items, let's take, for example, a flexible pipe. The requirements for installation of a flexible pipe are that you compact the subgrade below the pipe before you backfill, and then you backfill each continuous, and you compact each continuous backfill layer, structural fill. So you'll have a case where the installation specifications are in complete conflict with the environmental, let's call them regulations that would say do not compact the floor surface to ensure that we continue maintain that 1/2 inch per hour minimum infiltration rate. I think this is an interesting area. The impact of fine content and, more importantly, compaction could be looked at a little further. And this last one is a pet peeve of mine. On the left-hand side, you see the USDA, United States Department of Agriculture, soil triangle to classify soils. This is entirely appropriate and is what is used for topsoils. However, it is also often used for infiltration areas. Now, I think it is appropriate for topsoils, especially if you're using the rationale method, which is the method you use to calculate in your stormwater design flow, surface flows, and how you would come about assigning a runoff coefficient into the rationale method in the process of doing your surface flow analysis of the site. But when you're dealing with the infiltration, you're talking at the bottom of a detention pond or the bottom of an underground detention system, and almost by definition, they're going to be below the topsoil area. And I think it would be appropriate to use the unified soil classification method in there, and not the soil triangle, which is, as I said, for topsoils, which have a lot of root elements in it and organics and the like. And I don't think they're appropriate for the bottom of a detention system. And with that, no, I don't know how that slide got on there. I apologize. Maybe Jen put it on when she was updating this. That finishes the presentation. I hope you enjoyed it. I hope I didn't run over. And I'll turn it back to you, Tim.
Great, Terry. Like that third team there. Okay, so Terry, we've got a bunch of questions, and hopefully we'll have time for me to come back to your infiltration rate of 0.5 versus 0.014. So first, how would you clean sediments from the system?
Tim, you're breaking up a bit. Please repeat it.
Okay, sorry. Terry, how would you clean sediments from the system?
You would have to have inspection of the chamber floor and put people down there to collect it. It is not easy to collect sediments either in a detention system or even on top of a sand filter for any of these systems. So it's simply going down there, having confined space training for the people who are going down there, and using just standard tools to take the sediment collection up to the top. In the case of the sand filter, Tim, we place a geotextile on top of the sand filter. This is kind of an interesting thing. You're allowed to use a filter over the sand filter, but a geotextile over the sand filter, which replicates sand as far as the equivalent opening size of 40 to 100 microns, would be just about the same as the sand that was specified for the filter system. But they want the sand, the regulators, to do the work, but they're perfectly comfortable with the geotextile being placed over the sand. What in essence happens is the sediment collects on the geotextile, the non-woven geotextile, and we can take that out. And once we take that out, which is much simpler than scraping off the top 1 inch of sand and taking that up and replacing it after 4 or 5 years, we take that up through the roof and put a new geotextile down, and that's how we handle it.
Okay. Next is, this is more of a comment. If you have site soils with acceptable infiltration rates, blinding often becomes an issue and infiltration will fail. Then a sand filter is mandated. Again, more of a comment, but if you want to.
Well, listen, that last challenge I have for geotechnical engineers was pointed right at that topic, is how long are these systems going to be able to continue to infiltrate? and particularly in places like California, which has very, very, let's call them very good, progressive stormwater regulations. But in California, they have what's called a dead end system, which means that all the water is sent to the detention or the infiltration system, and there's no outlet, as opposed to, let's take New York, New Jersey, Pennsylvania. They require an overflow. So when the system is inundated, it can overflow. That's not the case in a dead end system. And if the infiltration starts to clog up over time, the water is just going to sit in there. There's no overflow. There's no mechanism to get the water out. So I do agree that that should be looked at closely, and the long-term infiltration properties of these infiltration systems. I don't know that we have the absolute answer to them yet.
Okay. Next is a question about stone requirement. Are you using less stone versus other systems for the underground storage?
Excellent question. The higher the profile, the less the stone. The lower the profile, the more the stone. Stone becomes very, very cost effective, especially at lower profiles, and geostorage becomes very cost effective at higher profiles because you can absorb the costs of the roof more. So it is it's kind of a floating scale on a job by job basis. Obviously, the cost of stones play a factor in that, but mostly it is the profile height of the system and the available footprint.
Yeah, I just want to make sure for the listeners, profile, you're talking about the depth or height of the chambers.
That's exactly right. Your
Correct.
Floor to your roof, the depth of the water height available.
Yeah. Next, thanks for sharing your knowledge. Very interesting. Any recommendations for the geomembrane? In addition, do you have to specify puncture resistance of the geomembrane?
Yes, I do, and that is where fabricated geomembranes will have a very a good performance in, because you think about it. Sometimes we don't know what the subgrade is going to be, and especially early on in the design process. But we're always putting 1.5-inch angular stone above it, which is pretty grueling. So many of the fabricated geomembranes have a very good they're robust, and their elongation properties are well suited for that. In addition to that, we specify a thick non-woven geo textile on the bottom and the top of these as cushion fabrics because of that stone.
Great. Do you, and this is my question, so for this listener, do you have a ASTM test method that you use for puncture, and what would be the typical requirement under that test method for the storage application?
Tim, I'd have to look at my specifications. That is not off the top of my head to recite an ASTM number on what it is. We do have it, but I can't tell you what it is offhand.
Great. Well, actually, that leads me to we're going to have a follow-up podcast, and we'll address that in the podcast.
I would be greatly interested in that.
Okay. Let's see, more questions. With the reinforced wall system being subjected to water infiltration, are there any provisions for addressing hydrolysis of the geosynthetics used?
We do have a specification on, and what we typically use is polyester flexible geogrids because of flow through them, as opposed to high strength geotextiles or rigid geogrids, which are harder to manage in a small confined space where you're building wrap walls. So there is a molecular weight and a carboxyl N group specification to ensure that we are going to have a good surface life with those materials.
Okay. This comes from the same listener. Are there characteristics of the geosynthetics that should be considered in the selection process? Also, the WWF baskets corrode over time. Are there provisions taken in to address this possibility?
Well, as I stated, we don't even galvanize the welded wire forms because they are just a construction tool to enable the compaction of the stone. Once the grid is, as I said, burrito-like, tucked back in and covered with stone, the geogrid is carrying the stone weight at the surface, and the welded wire forms are extraneous. So we're not counting on them for any structural support, and their design life is a matter of days. It's simply for construction.
Oh, okay, good. Let's see. Geotextile only systems. When booting inlet/outlet pipes, are you mechanically attaching the geotextile, or I guess geotextile to the pipe, GEP, geotext?
Yeah. Now you'd want to define that. Are you talking about at the entrance to the chamber or back at the protrusion through the perimeter liner system? At the perimeter liner system, if it is a detention system and we're using a geomembrane, we are most often attaching that to the pipe. But frankly, sometimes we're just using straps. I'm blanking on the name of it now, but booting them with stainless steel clamps.
Okay. So you mean like those stainless steel pipe clamps?
Yes, exactly.
Yeah. Right. Okay. All right, Terry, we're about 1:07 or 7 minutes after the hour. Do you want to try to tackle this infiltration rate, or should we just save that for the podcast?
You know what, Tim? I got all day, man. I'm bunkered down. Where am I going to go?
So just a quick thought on landfill cap versus the underground storage. The compaction, of course, on a landfill cap is very challenging on the slopes. So I'm not sure that they're able to meet that really low infiltration rate on the slopes. But I read you loud and clear about the difference being about 2 orders of magnitude.
Yeah, I was basing that, and your group knows this better than anyone. Hey, how often do they actually get the on-site or local soils to meet that infiltration requirement for the cap? And frankly, it's shockingly high. In my, it'd be a lot healthier business if it was really harder to meet that and they brought out more geomembranes rather than on-site soil. So that's what kind of perked my interest in looking into it, and I was basically surprised to see the just such a wide range of permeabilities that you see with small changes in the compaction effort, which is really not well defined out there. That's the part that no one really has defined. And obviously what is better defined is the small changes in the fine content, which, really, when you get above 10 or 12%, those a lot of those soils choke off. But the big one being, the compaction. People are going out there and they are, with their best efforts, being able to demonstrate that they are getting half an inch per hour infiltration rate or better. And my thought is, hey, with a little bit of compaction, that thing could drop not just twofold, but tenfold or 100-fold with just a pickup truck driving over it a few times, that sort of thing. So it's just an observation that I had that, boy, I know a lot of landfills are capped with on-site soils out there, and those same soils theoretically are being used everywhere, or hopefully being used for infiltration pads, and those two things aren't simpatico. I mean,
Yeah.
How the heck can you use those? How does that make sense? And I don't have an answer for it other than I think compaction the impact on compaction is huge. And I do think, as one of those questions indicated, the long-term infiltration rate of some of these systems, it's not geosynthetic based. It's not related to what I do. It's just an overall observation. I'm not confident 30 years from now you're going to maintain an infiltration rate that you measured pre-construction 30 years prior.
Yeah. Okay, Terry, so let's wrap up. I want to remind the listeners that we will have a follow-up podcast later this week. So if you still have any follow-up questions, please send them to fabricatedgeomembrane@gmail.com. And that'll be on the next slide, Terry. If you could move to the next slide.
Oh, sure. There you go.
Yeah. So under Jennifer Miller's name, you'll see fabricatedgeomembrane@gmail.com. Please send us those questions, and I will go cover those questions with Terry in this follow-up podcast. Thanks again to Terry Sheridan for an excellent webinar and joining us from Rumson, New Jersey. Terry, if you roll down to the next slide.
You got it.
Our next webinar is leak location surveys for containment applications. It is Thursday, April 16th, 2020 at 11 a.m. Central Time. The speaker is Matt Chemnitz, President of Leak Location Services. He gave an excellent presentation during the Geosynthetics 2020 conference just recently in Charleston, South Carolina. I think everybody's going to really enjoy that. And some new estimates of holes or defects per acre. So that's in April. All right, Terry, next slide. And finally, I encourage all the listeners to visit the FGI's website and see our other webinars and podcasts, specifications and guidelines, some installation details, technical papers and journal articles. We have videos on field and laboratory test methods under ASTM, a couple of leakage calculators, our events calendar, etc., as you see on the screen. That's fabricatedgeomembrane.com. So Terry, again, thanks for taking time out of your schedule in New Jersey to give us this excellent webinar. Be safe.
Always a pleasure, Tim.
Stay healthy. And
Same.
thank you to everyone who attended. Be safe and stay healthy. Thank you.